It should also occur to you that there will be situations where perhaps I want to find some present sum P, not the future, but I may want to find some present sum P that's equivalent to a uniform stream like this. Well, to find that, we know we can write the most general expression to be the following. That is, we will simply take each cash flow and discount it back as a single sum to time t sub 0 and add it all up, and you would get P, represented this way. This is the first cash flow at time t sub 1, discounted back 1 period, plus the cash flow at time 2, discounted back 2 periods, so forth, till you get to the last cash flow at time t sub n, which is discounted back n periods. Now, hopefully you can appreciate I could go through a very similar sort of algebraic manipulation of this formula to reduce it down to something far more concise. And the manipulation I would go through looks very, very similar to the one I just took you through for finding an equivalent future amount. Hopefully you can do that on your own. You can reduce this formula down to this concise expression, again, using the same sort of approach that I just did for the future amount. And it looks like this. So now if I want to find a present sum that's equivalent to a uniform stream represented as shown here, I can solve either this expression, and you'll notice this expression in the brackets is a function of only two quantities, the interest rate and the number of compounding periods, so I can also represent that one as an equivalence factor, find P, given A at interest rate I for n periods. As before, there will be situations where, in fact, we may be given P and have to solve for A. So all I have to do, of course, is take the reciprocal of this formula to produce this outcome. And I can represent this expression by the equivalence factor, find A, given P, at interest rate I for n periods. For example, what present sum P today is equivalent to the receipt of $100 each year for 3 years starting in the 8th period? Okay? There is no cash flow between 8 and 0. The first cash flow for my uniform series of $100 starts in the 8th period. And I want to know what present sum today is equivalent to that cash flow stream. A number of ways I can solve this. What we'll do first is we'll find a present sum P as of time 7 that's equivalent to that cash flow stream, because I have an equivalence model that will help me identify what present sum, present meaning relative to the occurrence of these cash flows, that occurs at time 7. And again, bear in mind, our equivalence model for the uniform stream, when we calculate that present worth, it gives us a present worth at the beginning of the first period of time. And the first period of time here goes from 7 to 8 because this $100 occurs at the end of period 8. So we will calculate a present sum for this cash flow stream as of time 7. Then we will treat this present sum as a future sum and then use my single cash flow model to take this cash flow and find its equivalent amount 7 years prior. And if you do the calculations, it looks like this. To find the present sum that's equivalent to that uniform stream as of time 7, it is $100 times find P given A. Let's assume you could invest at 12% per year, discounted 3 periods. That gives us a present sum as of time 7 of $240.20. But I want this amount back at time 0, not at time 7. So now I will treat this present amount as a future amount, use the single cash flow model, and move it back 7 periods. So I'll treat it as a future amount, $240.20, use the single cash flow model, find P, given F, and I can invest at 12% per year for 7 periods, results in $108.64. In other words, you would be indifferent between receiving $108.64 today or receiving $100 each year for 3 years, starting in the 8th period, provided you could invest at 12% per year. Let's take another model. This is called the arithmetic gradient series model. And this is a model wherein there are many situations in which we envision cash flows changing with time, and they change in a linear fashion. In this model, the first cash flow is G, or represented as an amount G, that occurs at time t sub 2. The next cash flow is twice G, or 2G. The next cash flow would be 3G, the next cash flow 4G, and so forth with this representation. And we'd like to be able to do equivalence calculations, say find some future sum that's equivalent to a cash flow stream like that, or perhaps a present sum that's equivalent to that cash flow stream. Well, hopefully, by virtue of the example I just went through, you can begin to appreciate we really don't need to calculate equivalence factors for these cash flow models to find both a future sum as well as a present sum, because once I have one or the other, I can use the single cash flow model to go in either direction. So if I was to develop an equivalence formula here to find a future sum, I can then use the single cash flow model to calculate its present sum if that's what I really want, or vice versa. So we'll just develop a factor only for calculating one value, and let's develop a factor that calculates a present sum that's equivalent to a cash flow stream that's represented this way. Again, to solve that problem, if I wanted to find a present sum that's equivalent to that cash flow stream, in theory, what I can do is simply discount each cash flow one at a time back to time t sub 0, add them all up, and I'll have that present equivalent. If I do some algebraic manipulation of that formula, what you'll end up with is an expression that looks like this. That is, this quantity here in the brackets is the more concise representation of the equivalence formula that I would write to discount each of these cash flows back one at a time. Again, you will notice that this particular expression is a function of only two things, the interest rate and the number of compounding periods. So I can tabulate that in the back of the book, and I can give it this equivalence factor representation. Find P given G when the interest rate is I and the number of compounding periods is N. Now, there may be situations where, in fact, we may want to be able to convert a gradient series like this to a uniform stream like this, and your textbook covers those scenarios. I just want to make you aware we can, in fact, write an expression to do a direct conversion of a gradient series like this to a uniform series like this. If you go through those calculations, you can write it concisely as this expression, and that, too, is tabulated in the back of your book, and given the equivalence factor representation, find A given G at interest rate I for N periods. Let's take an example. Let's assume we're considering the purchase of a piece of equipment. Let's also assume that we have done some estimates on what we think the costs of maintenance will be for this particular piece of equipment for the next 4 years. And our best estimates are it will be $3,000 in the first year, $4,000 in the second year, $5,000 in the third year, and $6,000 in the fourth year. Let's also assume that the supplier of this particular piece of equipment has made us an offer that we could purchase a service contract. And through the purchase of this service contract, we will pay them a fixed amount each period for the next 4 periods to be negotiated. And they will assume any and all maintenance costs that might happen to this particular piece of equipment. What we would like to know is, if I can invest funds at 8% per year, what is the maximum I should be willing to pay for this service contract? Now, bear in mind, that service contract is fairly certain. If I sign the contract, I will be committed to making those payments for the next 4 periods, but I'm far less certain, of course, about these cash flows. We'll get into the issues of uncertainty later in the course, but for now, let's just assume that we've estimated these cash flows and we're reasonably comfortable, reasonably certain those are the maintenance costs that will occur in the next 4 periods. What is the maximum amount A I should be willing to pay for a service contract for that supplier to pick up the obligation of taking care of those costs when they occur? There's a number of ways in which I can solve this problem. I'll do it two ways. First thing I'm going to do is I'm going to calculate a present sum P that's equivalent to this cash flow stream. Once I have that present sum P, I'll convert it then to an annual equivalent amount A over 4 periods. So let's calculate the present sum P first. That's the first step. It would look like this. Notice, as I look at this cash flow stream, I really have two component cash flows. What I really have here is a uniform cash flow stream of $3,000 each year for 4 years. In addition, I have an arithmetic gradient series shown by this triangular area, where the first cash flow in the arithmetic gradient series is $1,000 over and above the $3,000 that's a uniform representation, $2,000 at time 3 over and above the $3,000 which is represented as a uniform stream, and $3,000 over and above the $3,000 at time 4. So we're going to use two equivalence factors to solve this problem. We will find the present worth of this uniform stream and add to that the present worth of this arithmetic gradient cash flow stream. And I'll write it this way. The present worth is $3,000 as a uniform stream when I can invest at 8% per year for 4 periods, plus the gradient cash flow stream. And the gradient cash flow stream is the $1,000 that's increasing $1,000, $2,000, $3,000, 8% per year for 4 periods. I do the calculations, and it works out to be $14,586. That is, $14,586 is equivalent to that cash flow stream. But I need to have the uniform cash flow stream, not the present amount. So now I'll use my single cash flow model and convert this P to an annual amount A and write it this way. A is P times the expression find A given P at 8% for 4 years, and it works out to be $4,404. In other words, the maximum amount you should be willing to pay this supplier for them to assume the obligation for these maintenance costs would be $4,404. If the supplier offers you a service contract in which you have to pay, say, $5,000 per year, you should reject it. This is the most you should be willing to pay. But if they offer you a maintenance contract of $4,000 per year, you should take it. Now, I mentioned there's an alternative way in which I could have solved this problem. The way I just solved it was to find a present worth, convert the present worth to an annual worth. I could convert this cash flow stream directly to an annual stream, and if I did that, I'd do it in the following way. First of all, I already have part of the solution to my problem in that we already have a uniform cash flow stream of $3,000 per year. What I need to do now is to convert this gradient series right here, convert it directly to an annual amount. And I would write the expression the following way. The annual amount that I'm looking for this service contract is the uniform stream of $3,000 per year plus this gradient series converted directly to a uniform stream, and the gradient series was $1,000 converted at 8% per year for 4 years, results obviously in the same answer, $4,404. Let's talk now about the final of our 4 classic criteria, that is the 4 classic equivalence models that we'll be using. This one's called the geometric gradient series, and it's represented this way. There'll be many situations wherein cash flows will be changing with time in an exponential fashion. Inflation is a very good example. Inflation is a geometric phenomenon. That is, it increases as a percentage each year. It's not increasing in a linear fashion, but in an exponential fashion. And I would represent it this way. The first cash flow is represented as A1. The next cash flow at time t sub 2 is a function of the first cash flow having changed in time by a rate G. So the second cash flow is A1 times the quantity 1 plus G raised to the power 1. The next cash flow at time t sub 3 is A1 times 1 plus the rate of change of the cash flows raised to the power 2, so on until you get to the last cash flow. Now you'll notice here that I've represented this particular graphic where the value of G is greater than 0. That is, these cash flows are represented as shown here as increasing with time. It should obviously occur to you G not need necessarily always be positive. In fact, G could be less than 0, in which case you have a situation in which the cash flows are decaying with time. And it also should occur to you that sometimes G may be exactly 0, in which case what we have is the classic uniform series. In other words, the uniform cash flow model that we talked about just a few moments ago is really nothing more than a special case of this particular model. Again, we'd like to be able to find, say, present worth or future worths that are equivalent to a cash flow stream represented this way. And again, in the most general way we could write that is the present worth P, for example, is equal to the first cash flow, A1, discounted back 1 period, and then we will add the second cash flow represented as A1 times 1 plus G to the power of 1, discounted back 2 periods, so on until you get to the last cash flow stream. We could add that all up and you would have the result. Or I can do some mathematical manipulation on that particular formula, in which case you'll end up with this representation. It's not nearly as concise as some of the other equivalence formulas we've given you, but nonetheless you'll notice that it is a function of only 2 items, actually 3 in this case: the interest rate, the rate of growth or change of the cash flows over time, and the number of compounding periods. And again, I can tabulate this back in the back of your book, and I can give it the representation. Find P given A1 at interest rate I when cash is changing in time at rate G for n periods. For example, let's assume you plan to save 10% of your salary each year and invest it in an account at 8% per year. How much would you accumulate in the account in 10 years? Assume your current salary is $60,000 and you expect raises of 6% per year. First thing let's do, let's convert this problem description to its cash flow stream before I do any compounding, any discounting, before I try to solve for a P or an F or anything else. Let's just describe this problem in terms of what are the cash flows that are occurring each point in time. And it would look like this. The first year, we're going to save 10% of our salary. Our salary is $60,000, so we will save $6,000. Next year, our salary will go up, we expect, by 6%. We're going to save 10% of whatever that is, so obviously the amount I save each year also goes up by 6%. So the second year, I will save $6,000 times 1.06. The next year, it'll be $6,000 times 1.06 squared, and so forth out through the 10th period. What I'd like to know is, if I were to invest all of these funds at 8% per year, how much would I accumulate? That is, what is the future amount F that would occur by the 10th period by investing all of those savings? We can solve this problem a number of ways, and I will solve this one again in 2 parts. What we'll do is we'll find a present sum that's equivalent to this gradient series, this geometric gradient series. And then once we have the present sum, I'll use my single cash flow model to find F. And I would write the expression this way. P is equal to the geometric gradient series of $6,000 times my equivalence factor, find P, given A1, when I will be investing the savings at 8% per year, but my savings are increasing in their dollar amount by 6% per year over 10 periods. I do the calculations, and you find that present sum to be $51,148. But I want to know a future sum, so I'll use the single cash flow model, and I will treat that P to find a future sum, find F given P, when I can invest that present sum at 8% per year for 10 periods, and you'll see the result shown here. Let's summarize this lecture. We first talked about the purpose for equivalence formulas, and it was very straightforward. It's to simplify our equivalence calculations. Now, at this point, you may not think so. You've not yet had much opportunity to use these factors, but I think you'll find as you begin the opportunity to go through your homework problems and use these formulas, they do in fact facilitate many kinds, not all kinds, but many kinds of equivalence calculations. We went through 4 classic equivalence models. These are not the only models, but if you can understand the development and use of these 4 models, you can understand the development and use of any other models you may see. Specifically, we talked about the single cash flow model, and we developed 2 equivalence factors. We talked about the uniform series cash flow model, and we developed 4 equivalence factors for that one. We then talked about the arithmetic gradient cash flow series and developed 1 equivalence formula. And you may recall when we got to this point in the derivations, we said it really doesn't make a lot of sense to develop 2, 3, 4 different kinds of equivalence factors for each model, because once you've found a present sum or some future amount, from there we can use the single cash flow model to move it to any other point in time we so choose. We then concluded with a discussion of the geometric gradient cash flow series and gave it this equivalence factor. Equivalence. We'll be using that notion a lot throughout the remainder of the course. Again, the purpose of these equivalence factors, these equivalence formulas, is to help facilitate your equivalence calculations.